Okay, here's an example of how we work with work and energy and power. Now specifically here it's how much energy, how much work was done to push an object up an inclined plane. And I'm going to do this problem in two different ways. The first way is going to use the concept of work done is equal to force times distance, and that's assuming again that the force and the displacement or distance is in the same direction. If not, we can say that the work done is equal to the force times the distance times the cosine of the angle between the two. So let's make a drawing of this problem, but maybe we should first read it. That helps us understand what's going on here. It says here that a box with a mass of 20 kilograms is pushed 100 meters up a frictionless incline that makes an angle of 40 degrees with the horizontal. The box moves slowly at a constant speed. How much work did it take? So if it says that the box moves slowly at a constant speed, that means it's not speeding up. That means no energy is put into making it go faster, so no kinetic energy is gained. And the box moves slowly at a constant speed also means that there's no net force, that the force used to push the box up the incline counteracts equally to the weight of the box directed down the incline, so that there's a matching of forces there. So let's make a drawing that so you can see how that looks. So here's the incline. Let's say that the angle that the incline makes is equal to 40 degrees. Here's a box on the incline. Mu equals 0, meaning there's no friction here. So if we, for a moment, look and see what's acting on that box, let me draw the forces of gravity, and I hope this pen works. All right, there we go. So there's the weight of the box, mg, which means that there is a vertical component or a component perpendicular to the incline. This angle here, theta, is the same as this angle, theta, right there. So we can write this as mg cosine of theta. And here we have the corresponding component of the weight, which is parallel to the incline. And so we can write this as mg times the sine of theta. And then in order to push the box upward, we're going to need a force. And let's assume that the force is parallel to the plane. There's the force F. And of course, if the force, or if the box is going to be pushed up the incline at a constant speed, that means that this force must equal this force, so there cannot be a net force and no net acceleration. You may say, well, if there's no net force, then how can the box even start to move? And that's, of course, correct. You need to get it started, but once you add a little extra force to get it started, then you can back off from the force a little bit and make F exactly equal to mg sine theta, and then the box will just continue to move up the hill. And then the question is how much work is done. And so if the distance covered in an incline is 100 meters, so if the displacement equals 100 meters, then we could say the work done is equal to the force required to push the box upward at a constant speed times the displacement of the box. And the force, of course, in this case must be equal to the mg sine theta. So in this case, we can say that the work is equal to mg sine theta times the distance. And now we're ready to plug in the numbers to figure out what that is. So work is equal to the mass, and we said the mass was 20 kilograms. The acceleration due to gravity, 9.8 meters per second squared. The sine of 40 degrees. And then the displacement, 100 meters. Notice units-wise, kilograms meters per second squared, that's the same units as newtons. And then we have meters, so the answer will be Newton meters, and we know now that Newton meters is the same as joules. Where's my calculator? Here we go. So we have 20 times 9.8 times the sine of 40 times 100. And that gives us work done equals 12,000, let's round it off to 12,600 Newton meters, or that's equal to 12,600 joules. So again, we use the principle of work done is force times distance. But there's another way in which we can do a problem like this, because essentially what happened is that we started at some particular place, and eventually the box ended up at a different place. It ended up higher than it was before. It gained height. So there's a change in height or an increase in height. And any object that increases height increases or gains potential energy. So we could also say that the work done is equal to the change of the energy put into the system, or in this case, put into the block. And in this case, the change in energy, it's not going to be kinetic energy because it's moving at a very slow, constant speed, so there's no gain in kinetic energy, but it's gained height, so we could say it's actually gained potential energy. So this is equal to the change in potential energy, and by definition, the potential energy is mass times g, the acceleration of gravity, times height. So this is equal to the change in mgh. And of course, the mass isn't changing, g isn't changing, h is changing, so we can say that's equal to mg times the change in the height. And oh, there we go, there's my pen. And so therefore, we can say that the work done is equal to mg times the change in the height. So how much did the height change? If we look at this triangle right here, there's the triangle. Height is the vertical side of the triangle. The hypotenuse is the displacement. So using trigonometry, of course this being the angle theta, we can say that the opposite side h is equal to the hypotenuse, which is the displacement d, times the sine of theta. So the height gained is the displacement d times the sine of theta, because that's the opposite side to this triangle. And then plugging that into our equation here, we can now say that the work done, which is equal to the change in the energy, or change in potential energy, is equal to the mass of the object, 20 kilograms, times g, which is 9.8 meters per second squared, times the change in the height, and the change in the height is going to be the displacement times the sine of theta. So the displacement times the sine of theta, and then if we plug in those numbers as well, you can see that you end up with the exact same equation. Work done is equal to the 20 kilograms times the 9.8 meters per second squared, times the displacement, which in this case is 100 meters, times the sine of 40 degrees. And again, you'll get the exact same answers we did before. That would be 12,600 joules. So you can see that you can find the work done in two different ways, using the equation force times distance, or force times displacement, and the equation, the change in the energy. Now that we have kind of the concept here, let me show you how we can actually expand upon this and come up with a general way to solve a lot of these energy, work, and power type of equations or type of problems. So let me put another example on the board.